In this lecture, we will solve the problem 7.7 of Griffiths 4th edition, Introduction to Electrodynamics. The problem 7.7 is a metal bar of mass m, that is this metal bar mass m, slides frictionlessly on two parallel conducting rails. These two parallel conducting rails, which is L apart. Distance between them is L, as shown in the figure. A resistor R is connected across the rails, and the uniform magnetic field B pointing into the page fills the entire region. Now, as I said, there are four parts. Part A, we will see. If bar moves to the right at the speed v, the bar moves at the uh, speed v along this x direction. What is the current in the resistor? In what direction does it flow? This velocity, is moving in the x direction. This is equal to tx over dt. The script E, that is the induced EMF is equal to minus T pi over Tt. That is a time derivative of the magnetic flux. Magnetic flux is equal to minus PL Tx by dt. Because here the P is constant, L is constant, only X varies with respect to time. So Tx by Tt is V. Don't worry about the negative sign. This, after all, will indicate the direction of flow. So, script E is equal to PLV. IR is equal to, that is, E is equal to IR, which is equal to PLV. So IR is equal to PLV. That means I is equal to PLV over R. I have brought this R to the other side. This is the current flows across the resistor. In this case, V cross P is upwards. Using left hand rule, we can easily trace that V cross P is upwards. So naturally, current is downwards. This is the equation for current, and the direction of the current is downwards. Now, the section B is what is the magnetic force on the bar, in what direction it will be. So F is equal to, by definition, I into L into P. We just now we have seen I is equal to PLV over R. This is what we have seen in part A. And this I multiplied by L into P. So here there is a P into P squared, and L into L become L squared V over R. And what direction? This is the force. This force is, according to left hand rule, this is along the left direction. Then section C is, if the bar starts out with the speed v naught and the time t equal to 0 and is left to slide, what is its speed at a later time? That is, we have to find the time derivative of the velocity. So from here we have seen F is equal to, of course, actually here we have ignored the negative direction. So this will be in negative direction. So minus sign indicate the direction. So which is F is equal to, from the section B, P squared L squared V over R, which is equal to Newtonian mechanics. Force is equal to mass into acceleration. This acceleration is equal to rate of change of velocity, Vt, dv over dt. So m dv dt is equal to minus this one, p squared L squared over R V. Then if you bring this m to the other side, dv by dt is equal to minus p squared L squared over mr, because we brought this m to the right hand side. So this entire thing, you keep this entire thing as alpha. P squared L squared divided by MR is alpha. So this will become minus alpha V. So naturally, if you integrate it, you will get V of t is equal to V naught, where V naught is the integral constant, e power minus alpha t. Now we will move on to section T. Now the section T is the initial kinetic energy of the power was, of course, uh, of mv naught square. Check that the energy delivered to the resistor is exactly the of mv naught square. So now power delivered to the resistor is rate of change of work done, that is TW over TT, which is equal to I squared R. In section A, we have seen I is equal to PLV over R. Then I squared, we are squaring it, and we have to multiply this by R. If you multiply the denominator will become R squared R will get cancelled, you will get simply R. This will become P squared L squared V squared over R. So now what we are going to do is, we have seen already P squared L squared over MR is alpha we have taken for mathematical simplification. That means we have to divide and multiply by M. Then this numerator, which this parameter which I have shown in violet color, this is alpha. So the rate of change of work done is equal to alpha times m into v square. From earlier section, just previous section, section C, we have seen V of t is equal to V naught e power minus alpha t. So you substitute it here. So V naught will become V naught square, and this exponential term will become e power minus 2 alpha t. Already there is alpha m. So now you have to integrate with respect to time. So only exponential term contain time. So all other term I am taking out. Alpha m v naught square I am taking out. I am integrating only the exponential term between 0 to infinite. So e power minus 2 alpha t tt is, if you integrate, you will get e power minus 2 alpha t divided by minus 2 alpha. So you have to apply now the limit. If you apply the upper limit, e power minus alpha will become 0. If you apply the lower limit, e power 0 is 1. So this will become 1 over minus 2 alpha. So here this minus and minus will become plus, and this alpha will get cancelled. This alpha and this alpha will get cancelled. So inside the bracket you have half. Then here you have half m v naught square. So we are integrating, so the left hand side will become work done. So exactly we have proved that the energy delivered to the resistor is exactly of mv naught square. So thank you very much for your support and watching my videos continuously. Thank you very much.